Good morning or good afternoon, depending on where you are. My name is Professor Duke Orata. We are continuing with our lectures in thermodynamics. Today we want to look at heat conduction in a pipe. So if we think of radial steady-state conduction in a pipe of unit length and consisting of several cylindrical surfaces which are concentric to the axis of that particular tube or pipe, let us just write that down. So considering radial steady state a transfer in a tube of unit length and consisting of several cylindrical surfaces concentric to the axis of the tube or pipe. Concentric to the axis of the tube or pipe. So we are saying we have this pipe which is of unit length and it consists of several concentric cylindrical surfaces concentric to the axis of the pipe. What do we mean by that? So we have this profile. My circles might not be the most symmetrical, but I'll try to get them as symmetrical as I can. Cycle, which is so symmetrical. One. The other cylindrical surface is that one. Let's put that one as the other one. And let's put that one as the other one. They are not perfect cycles. They are not perfect circles. But they'll be able to explain the point. They'll be able to explain what you want to say. So we are saying this tube consists of several cylindrical surfaces and they're concentric to the axis of the tube. In other words, think of this tube. Let's think of it as an extension there. And think of that as its axis. And these tubes are all concentric to the axis there. So let's call that radius 1. For the second cylindrical surface, let's call that radius 2. For the third cylindrical surface, let's call that radius 3. And for the fourth one, radius 4. So we're assuming that the heat transfer in this system, the radial heat transfer, is a steady state heat transfer. What does that mean? One, we have always talked about no accumulation of energy, no accumulation of material. And what it means, in a nutshell, is also that the rate of heat transfer is constant. And number two, we are assuming that on these cylindrical surfaces, the temperature is uniform. In the cylindrical surface itself, the temperature is uniform. In other words, the surface is isothermal. So let's just note that. We are saying that the rate of heat transfer is constant, and we are assuming that the surfaces, the cylindrical surfaces, are isothermal. Very important for us to note that. And so when we have our system like it is, let us say that we have this particular system. That's one to illustrate again, so that we see the temperature gradient. That's not the best circle, but it suffices. So that if the thickness of this pipe or tube is dr, if the thickness is dr, then we can represent the temperature gradient. Let's have that as our curve there. Let's have that as our temperature gradient. Let's call that dt. So our temperature gradient, dt over dr, can be captured graphically in the manner in which you're shown. The thickness is dr, and then of course the temperature gradient is dt. Temperature gradient is dt. And number two, like we have said, that for this tube here, the cylindrical surfaces are isothermal. So let us say that this particular one, whose radius is R1, as temperature T1, the other one whose radius is R2 as temperature T2, the one whose radius is R3 as temperature T3, and the one with the radius R4 as temperature T4. And we can categorize them and call this A, B, and C. So that as we apply those equations, we don't do it ambiguously, so that you're able to follow what we're talking about. Remember, in our lectures, we talked of a multi-composite system consisting of 3 walls. So I encourage you to look at that particular lecture so that you're able to relate to what we are talking about here, because you're going to relate it at some point. Now, if we apply Fourier's heat law to this particular system, taking cognizance of the fact that the temperature gradient dt over dr, based on our model there, we note one or two things. That we are assuming that R1 is greater than R2, is greater than R3, is greater than R4. So what is the import of that on the temperature gradient? It means that the temperature gradient for R1 will be greater than that for R2, greater than that for R3, greater than for R4. For the simple reason that, remember, we are dividing with the R. So when R is big, that will be small. So R4 is greater. So we are saying that the temperature gradient decreases as we move to the outer cylindrical surface. Important to take note of that particular fact. So if you now apply the Fourier's heat law, so if you apply heat law, we remind ourselves, what was it? The rate of heat transfer, Q, is given by minus thermal conductivity, the area of flow, and the temperature gradient. Remember, rate of heat transfer or heat flux density effect of heat transfer. This is thermal conductivity, coefficient, that is area of flow, and that is the temperature gradient. And that is Fourier's law. You're already familiar with it. And once more, I repeat, please go through the lectures which you have covered, and we have talked in detail with respect to some of these quantities. And it's very important for continuity in understanding to flow together with all the concepts. Now that we have gotten that, so what happens to our system here? What happens to a system? We have Q, we have K, we have area, we have that. Now, the surface area of this pipe, think of that pipe. Think of it that way. And we have said it has length L, which we call unit length, so that we might not have to keep on carrying the length, so we assume it's unity or 1. And then it has an area. That's the radius. So if you open this pipe, open it, then you will see that for this particular pipe, the surface area will be 2 pi r times L. That will be the surface area. That particular pipe. When you open it up, that will be the surface area of this particular pipe. That is 2 pi r times L. 2 pi r times L. That is basically what is 2 pi r. That is that length there, the circumference, times that length. That will give you the area. Now, let us now move up with our use of Fourier's heat law. So if you apply now Fourier's heat law, then it tells us that Q will therefore be equal to minus K into the area of flow now, which is that, will be 2 pi RL into dt. And what is our x here? That's now the radius. X now corresponds to radius, dt. So if we do a few rearrangements, this expression here, so on rearrangement, we will have Q, the R over R, the R, we've taken the R that side, R, taken R the other side, so we are left with minus K, 2 pi L dt. So if you integrate, for example, if you integrate from temperature 1 to temperature 2, which is radius 1 to radius 2 as our limits, then on integration, where I use the identities, just in case you have forgotten. The identities I'm going to use is 1 integral of dx over x is natural log of x plus c. Of course, because you are not put the limit, so you have to have the integration constant. And then I'm also going to use, in this particular case, I'm also going to use the identity integral of dx is x plus c. These are the ones I'm going to apply here. So apply that there. So we have q integral of r1, r2, the r over r is equals to minus k 2 pi l dt t1 t2. Very straightforward. We simply just applied the Fourier laws to the system. And of course, remember, if you look at when you work with the multi-composite system of the several walls, Then you do the same for T2 to T3, T3 to T4. That's why I said I encourage you to go through those earlier lectures. Now, that is what we have. So if we sort out this using the identities there, then we have that Q, into natural log of R2 over R1 will be equal to minus K into 2 pi L T2 minus T1. So if we solve out for Q, then Q definitely is equal to minus K 2 pi L T2 minus T1 over natural log of R2 over R1. Now, if we look at the global behavior of heat transfer in that pipe, let us take just globally, say that we have this pipe. The temperature in this pipe here is TA. Temperature outside the pipe there is TB. Let's do it in a more refined way. So let's say for the inside pipe, for the outside pipe. For the inside pipe, temperature is TA. The coefficient is HA. The outside pipe is TB. Coefficient is HB. So for this particular system, in general, Q here will be simply that overall heat transfer coefficient into, let's be consistent, let's call it U. Overall heat transfer coefficient, which you call T, minus, that is TB minus TA. The overall heat transfer coefficient would simply be minus U of T, that is UT, overall heat transfer coefficient, times the change in the temperature. The inside temperature is TA, the outside temperature is TB. And of course, you know this overall heat transfer coefficient is a summation of several of those coefficients. If you go back to one of those lectures, we say that UT, the overall transfer coefficient, 1 over UT, we said it was delta X over K, sum of that. We said that was overall heat transfer coefficient. When we talked of the composite boundary, multi-walled system, where we had several walls and we said they're made of different materials and so forth and so forth. So I kindly encourage you to look at that earlier lecture. So now, when we relate the two, because they're equal, then we have that minus U into TB minus TA is equals to minus K 2 pi L T2 minus T1 over R2 R1. So ignoring this temperature changes, cancel out. So we'll have that UT, overall heat transfer coefficient. The only thing we're interested here, the overall heat transfer coefficient in this particular systems will be equal to K. The negative signs will go, so it will be K 2 pi L over natural log of R2 over R1. But remember, in the overall heat transfer coefficient, we have the individual heat transfer coefficients corresponding to the various surfaces in that particular system. One from R1 to R2, R2 to R3, R3 to R4. We saw that in the multi-walled or the composite transfer of heat in composite system consisting of several walls. So we know that this has just confined itself to transfer from R1 to R2. The transfer from R1 to R2, R2 to R2 to R3, R3 to R4. So let us now take care of that. Remember, we had said that our Q for the global system was minus UT into TB minus TA. Now, our outer one and the inner one are T1 and T4. So that will be T4 minus T1. And so if we factor in these quantities, where we have that, then the total, the overall heat transfer in that system will therefore be given by T4 minus T1 times 2 pi L, 2 pi L into T4 minus T1. T4 minus T1, remember that's unit. This is 2 pi, those are just constants. This is the outermost temperature. This is the outermost cylindrical surface. This is the innermost cylindrical surface. And of course, that thermal conductivity will be relative to the surface. So we will have divided by, remember, that is UT. So we can take that down, that you don't have that coefficient up there. So we'll have it as natural log of R2 over R1 corresponding to K for A. And then we have plus natural log of R2 over R3 over R2, corresponding to K, B, the thermal conductivity for that B, and finally plus natural log of R4 over R3 over the thermal coefficient associated with C. So this gives us the expression of the rate of heat transfer in this pipe consisting of cylindrical surfaces concentric to the axis. And number 2, we have assumed radial steady-state heat transfer. In other words, the rate of heat transfer is the same, is basically the same, and that those surfaces are isothermal. And so this gives us the expression of heat conduction in a pipe consisting of concentric cylindrical surfaces. The cylindrical surfaces are concentric to the axis. In other words, their point of origin is in the axis of that pipe. And don't forget, one thing which you better never forget is that the heat is transferred perpendicular to those surfaces. The heat is transferred perpendicular to those surfaces. That's the basis of Fourier's heat law. Heat is transferred perpendicular to those surfaces. So let's stop at that point. We'll pick up later in other lectures.